Good morning, everyone. I'm glad to welcome you to this webinar, which is the second webinar of the COACCH Project series out of 4, and which is part of the broader set of webinar organized by the Euro-Mediterranean Center on Climate Change, CMCC. Who's speaking is Francesco Bosello. I'm Professor of Economics at the University of Milan, the Department of Environmental Science and Policies. I'm also senior researcher here at CMCC, and I'm coordinating the COACCH research project. So before giving the room to our speaker that are going to introduce a very interesting, hopefully for you also, not just for ourselves, the very interesting topic of climate change impacts on labor productivity and energy. Let me very briefly tell you something more about this COACCH project. COACCH stands for co-designing the assessment of climate change costs. Basically, this is a Horizon 2020 research project who's going to last 3.5 years. It is slightly more than 2 years old, so we have passed the half-life of the project and we are finally seeing the end of it. What are the major aims of this project? The project would like to improve our knowledge about the environmental and social economic implication of climate change. What are the two major novelties of this project? First of all, that we are trying to address as much as possible economic and macroeconomic consequences of climate change with a sub-national perspective. So we would like, while keeping the broader overview of what is going on globally, increase the resolution, the detail of sub-national or regional consequences of climate change. This in order to highlight as much as possible hotspots. The second novelty is related to the consideration of what we call the social economic tipping point. So we would like to emphasize and detect as much as possible those impacts that are non-linear, which are discontinuous, that could be locally, for instance, cause disproportionate or very huge impact. So we would like to understand the distributional implication and asymmetries of climate change impacts. This said, let me also very briefly say some words about CMCC. Perhaps some of you are not new to these webinars, so forgive me for the repetition, but some could be new to this. CMCC is kindly hosting our webinars within their broader series of webinars. What CMCC is a multidisciplinary research center, Italian research center, has been founded in 2005, has been transformed into a research foundation, so it's absolutely no profit. In 2015, gathers CMCC all the knowledge and the different skills that we have here in Italy on climate change, with the aim to provide and improve and provide support to research, to policy making, and also to businesses, including the issue of climate change in the broader context of sustainability and sustainable development under a societal point of view. In addition to being a multidisciplinary research center, it is also a multi-office research center. You see here that our offices are spread more or less all over Italy, including major islands. CMCC is organized in research divisions. What we call division are basically research departments. Being multidisciplinary research center, the divisions are disciplinary in the sense that they address the climate change issue under its multidimensional perspective. So skills and competencies goes from climate science to oceanography to crop and land use modeling up to social economic disciplines. As the division are multiple, also the topics that we treat are multiple. What is nice of CMCC is the huge integration and interaction across the research division. Let me say that actually CMCC is founded and composed by 7 members that are either a research institution or academic institution. Let me recall them very quickly. The National Institute of Geophysics and Volcanology, the University of Salento, the Italian Aerospace Center, the Ca' Foscari University of Venice, the University of Tuscia, the University of Sassari, and the Politecnico of Milan. In addition to research, CMCC strongly support outreach and dissemination activities. These webinars are just one of these dissemination activities, but CMCC also develop other events like workshop, conferences, of course the scientific publication of its researcher, but also communication and educational activities. And with this I've finished the introduction. Let me just recall that you can actively participate to the webinar, raising questions to our speakers. Unfortunately, you cannot speak to them, but you are kindly invited to write your questions. I will read them, and of course I will try to select to the best of my capacity the questions and address them to the speaker. So you have this question tab on the right panel of your of the, let's say, the windows of the GoToWebinar facility, and you can use that. I will read the question and pose them for you to the speakers. Let me also recall that the webinar will be recorded, and you can find it on the CMCC website. So you can have the opportunity to listen to it afterwards, or also invite someone else to do it if not being able to participate directly today. And very last, let me also invite and anticipate the next webinar on next May 18, which will be dedicated to the presentation of the Climate Adapt catalog, Climate Adapt, the European Environmental Energy Portal on adaptation, a very useful and interesting tool to address that specific topics. And with this, I just would like to give the floor to our speakers. First to Dr. Shouro Dasgupta, then Jessie will pop in, and they are working in COACCH work package 2, which is the work package that analyzes basically all the climate change impact with a sectoral perspective, let's say. So Shouro, I think that the floor is yours for a very short introduction, and then we can start. Thank you, everyone.
Thank you, Francesco, for the introduction. And thank you, everyone, for joining in wherever you may be. I'd like to begin by wishing that everyone and their families are safe. So, as Francesco said, COACCH set out to conduct the most ambitious investigation of multidimensional and multi-sectoral climate impacts. And as part of this project, Task 2.4 analyzed climate change impacts on energy supply and energy demand, and of course, labor productivity mostly in the context of European Union. Our plan is pretty simple here for this. First, we estimate historical response functions using econometric methodology, and then we combine these estimates with future climate scenarios for projections under various warming and socioeconomic scenarios. The ultimate goal of these impacts is to use them as inputs to a regionalized CGE model, which is the crown jewel of this project and is being developed by Gabriele Standardi, Francesco Bosello, and Romero Parado. So with this short introduction, I will ask Jessie Schleypen from Climate Analytics to present the first paper on climate change impacts on labor productivity in EU. Jessie?
Great. Thank you, Shouro. So I will present now the climate change impacts on labor productivity that it's a product of this project, COACCH. So just a brief background on why we want to study the EU and how, given the existing studies, how is it impacted by climate change? So first, the EU is a very important part of the global economy. It contributes more than 20% of the global economy, but it's still at risk of climate change. So based on previous studies, the impact to climate change could amount to 190 billion under a business as usual scenario. And this impact could be lowered down to 120 billion or 1.2% of the current EU GDP, given a 2-degree scenario. Further on, there's also a study that says the labor productivity in Southern European countries, which was said to be the most at risk of climate change, could decline by 10 to 15% under a high warming scenario. And again, a lot of the impacts could be avoided with more mitigation leading towards a 2-degree scenario. So how do we want to add to these existing impact analyses? So as Francesco said, the objective of COACCH is really to have a more downscaled level of assessment of impacts. And so we now look not only on a country level impact, but on a subnational level impact. So there would be discrepancies within countries. So for this, we used economic data of 255 NUTS2 regions in 28 EU countries. So we did the analysis prior to this year. And the data set allowed us to see information from 2000 to 2015. Alongside this economic data, we also use high resolution climatic data from GLDAS of historical climates for each of the regions. And we use these together with climate projections from the Eurocordex. So basically, we use 2 different warming pathways. So the more moderate warming would be RCP 4.5, and the more extreme warming would be RCP 8.5. So as Shouro already summarized, the methodology is basically to use econometric methods to estimate a historical sectoral optimal condition for labor productivity, and then apply these resulting elasticities to climate projections in order for us to have a projection of economic risk per sector. So just briefly on this econometric framework. So we use a nonlinear panel fixed effects model. As you can see on the left-hand side, this would be our dependent variable, which is the sectoral GVA or gross value added per economically active population. So for the sectors, we have considered agriculture, industry, and services. And within industry, we isolated construction as a very exposed, outdoor exposed sector. And on the right-hand side, you can see we really want to focus on temperature impacts to economic activity. So here, our main variable of interest is this mean annual temperature. So we do a squared form of this mean annual temperature. So we also capture nonlinear responses. And also a vector of control variables. So we also included precipitation, maximum temperature interacted with income groups. So basically, we wanted to see if the response of economic activity is different for high income groups and middle income groups. And then we also wanted to see a deviation of annual temperature to a 4-year moving average. So this indicator is more towards the short-term changes in temperature. And then the warm spell duration index, which is our indicator for heat waves. So this is the number of events wherein there are 6 consecutive days that the maximum daily temperature exceeds a 90th percentile threshold. And other than these control variables, so we can control for other region-specific indicators that we cannot really explicitly all declare in the equation. We put a time invariant regional fixed effects, as well as a region-specific time trend. So from this, from the econometric framework, there is an issue normally for subnational analysis to have this spatial interdependence. So this violates an assumption that the data is independent and identically distributed. So in order for us to control for these spatial dependence, so from region to region, we apply spatial econometrics. So what this does is that we not only take, let's say, the climate variable for a specific region, so the reaction of the economic activity within a region reacting to its own climate variable, but also a weighted average of its neighbors. And the neighbors are basically determined by this threshold that we put 150 kilometers around the region. So this is called the spatial Durbin model because we also control not only for spatial interaction for the independent variables, but also the dependent variable. So just to make it a little clearer with this slide, you can see how the setup is. So here you can see that we have included in the equation the let's say the temperature variable for the specific region, but also a temperature variable that represents the temperature around the region. So a weighted temperature of the region's neighbors. Okay, so just to move on to the results. So you can see here that this is the result that we have for the different sectors, and you can already see that there is a difference sectorally on the optimal temperature, which is basically what we observe to be the temperature that reaches the highest productivity. So for instance, for agriculture, regions that tend to have an annual mean temperature of 8.3 degrees tend to have a higher labor productivity. And for construction, it's 10 degrees, and for industry is 10.8 degrees. And so from this, you can see that agriculture is very sensitive to higher levels of, or would tend to have impacts as temperatures increase. And you can also see from the shape of the curves. So for agriculture, so towards the optimal temperature, it's very slowly increasing the productivity, but after this optimal temperature, the curve is rather steep, which means that the higher the temperature, the greater the losses for productivity. When you compare this to construction, let's say this is rather a flatter curve. So the the changes in labor productivity for every change in, or every unit change in the mean temperature is rather gradual. For industry, you can see that this is rather slightly opposite than agriculture, that it's a large increase in labor productivity towards this optimal and a gradual decrease. So from here also you can infer that with climate change in the future, and as we go towards higher mean temperatures, then agriculture is definitely something that is very sensitive to this. Okay, so further results. So as I said, we also added some control variables, and this may be also interesting for some of you. So the WSDI is our indicator for heat waves. And as you can see, this is the decline in agriculture is 0.2% for every increase in this indicator. So for every increase in events of heat waves. And for construction, it's rather more, 0.3% decline in construction and industry. In terms of the short-term temperature deviation from this 4-year moving average, we see that the productivity in industry is 1.1% decrease, and services is a larger decrease than industry, which kind of signals that it has higher risk of sudden changes in temperature in the short run. And lastly, our interaction of income group and maximum temperature, we see that high income regions have lower impacts only in industry and construction, but we don't see the same thing for the other sectors. Okay, so these are the projections that we have, and what you see here is a map of Europe under the high warming scenario around year 2070. As you can see here, the decline in agriculture productivity is about 10.2%, construction is 6.6%, and industrial productivity is about 4.3% for the whole region. In contrast to RCP 4.5, which is a more moderate warming scenario. So this you can already see a large decline in the impacts. So for agriculture, it's only 8.6%, construction is 3.1%, and industry by 2.7%. And you can also notice how the impacts are rather larger in general towards the south, and in the north is more, you don't really see so like a one-way impact. So climate change always has the negative impact, but there is also some gainers around the north of Europe and around the middle here. So just a summary of this sub-national impacts that we did. So the main losses are really seen in Greece, Italy, Spain, and Bulgaria, but these are specific regions in these countries. And if you can notice, so this is the advantage of having a subnational analysis, that you can have both gainers and sufferers in the same country. And what we also found in our research is that, for instance, Basilicata is one of the regions with the lowest GDP per capita. And for the parts of Italy, let's say Trentino Alto or Valle d'Aosta, these are rather starting off with the current, so the current temperatures are relatively cooler than other parts of Italy, but also they also have very advanced green technology. So this part of Italy, actually Trentino Alto, based on our research, this is also heavily agricultural, and it's a good thing to see that they are gaining in terms of agriculture, even with these scenarios. For industry, so these are again similar regions, but in some cases these are different parts of the country. So for Spain, let's say if you see the agriculture, Spain is the region of Murcia, and here the region of Andalusia is at risk of industry and construction losses based on our research. Yeah. So I think that's it, and we will conclude at the end of the next presentation. Shouro?
Thank you, Jessie, for the wonderful presentation on labor productivity impacts. So now we will switch tracks and move to how vulnerable global and European hydropower generation is to climate change. This is a joint work with Fabio Farinosi from JRC and Erika Dachan from University Ca' Foscari and CMCC. So hydropower represents the main renewable source of electricity production for many countries across the world. The global average share of hydropower generation is about 34%. We investigate the impact of both gradual and extreme climate change on hydropower generation. The hydropower generation data comes from NR We have data for 145 countries for 1971 to 2016. We first estimate historical responses and then use this impact response functions, combining them with future climate data to investigate and project the future impacts. Some descriptive statistics, I will not spend too much time on this, but as you can see, hydropower share is significant across the world. So some trends. Share of both hydropower and oil generation has declined. However, it's still a significant portion of country-level power generation. The climate data we use is again GLDAS, which is available at 0.25 degree spatial and 3-hourly temporal resolution. We use mean, max, and average temperature, total precipitation, standardized precipitation index, and warm spell duration as our stressors. So SPI, or standardized precipitation index, informs about the stock effect due to potential variation in runoff volumes stored in reservoirs over long time periods, either due to prolonged wet or dry periods. We'll give more details on this as we go along. So the general econometric framework, we use a panel regression with country and year fixed effects, where the dependent variable is the log of annual hydropower generation. As I mentioned, we use mean temperature, total precipitation, and 3 different measures of SPI, the 6, 12, and 24, so short-term drought events, medium-term drought events, and of course, long-term drought events. But we also control for a vector of other explanatory variables, including installed hydroelectric capacity, final electricity consumption in a given country, the share of hydropower capacity, and of course, the different electricity production mix. So essentially, the other sources of electricity generation in a given country, whether it may be from gas, oil, coal, or nuclear. And as I mentioned, being a panel econometric framework, we use time invariant country fixed effects and both linear and quadratic time trends. Some of our variables are non-stationary in nature, but they're co-integrated. So we run a first difference regression, but also as robustness checks dynamic OLS and an error correction model. For the sake of timeliness, being on time, I will only focus on results from the first difference regression in this webinar. So this is the table. As you can see, that mean temperature has a persistent negative impact on hydropower generation, and all the SPIs as controls for drought events also have negative persistent impacts. If you can see at the bottom, with the RMSE score, we find that the specification controlling for the 12-month SPI, so a medium-term dry event, is most robust. So what does this table mean to us? So what we see is that a 1 degree increase in mean temperature results in between 0.025 and 0.03 percentage point decline in hydropower generation, depending on the specification. One additional long-term dry event reduces hydroelectricity generation by between 0.16 and 0.17 percentage point, whereas a more medium-term dry event reduces generation for small units by more than 0.3 percentage points. For short-term dry events or drought events, we see that an additional drought event reduces hydroelectricity generation by almost 0.4 percentage point. So these are large and persistent impacts across over time and across countries. We also control for precipitation, which has a inverse U-shaped relationship. So as precipitation increases, first it has a positive impact on hydropower generation, but beyond a threshold, we see negative impacts. So we combine these historical estimates with future climate data by combining this with various warming scenarios. We focus on RCP 4.5 and RCP 8.5, which are simulated using 5 different climatic models. We define current climate as a 20-year time period between 1986 and 2005. We define a future medium-term event as 2030 to 2050, whereas a long-term climate change future event is defined as a 20-year period between 2050 and 2070. So these are global impacts. So I'll first present global impacts and then move on to European level impacts. So under RCP 4.5 by 2050, we expect hydropower generation globally to decline by 3.6 percentage point. As you can see, mostly negative impacts across the world. Whereas by 2070, under 4.5, we expect the global decline to be about 5.3%. For RCP 8.5, which is an unmitigated climate change scenario, we expect by 2050 global hydropower generation to decline by 4.2%. For RCP 8.5, by 2070, so a longer term event, we expect global hydropower generation to decline by more than 7%. So these are persistent and long-term negative impacts on hydropower generation, which, as you recall, is still a significant share of electricity production across the world. So the biggest producers of hydropower also stand to lose out the highest due to climate change. Brazil, under 8.5, is expected to suffer about more than 6% decline in hydropower generation by 2070. China is expected to suffer 7.4% decline. Russia and US, more than 7.5 and 10% decline under RCP 8.5. Now, the case of Europe. We combine our estimates with future high-resolution climate data for Europe as well. And we find that the highest losses will be in the Nord-Norge region in Norway, north and eastern parts of Finland, and the upper Norrland in Sweden. These are large impacts, even in Europe, which is known for adaptation and mitigation across the world. Country level impacts for Europe by 2070 under an unmitigated scenario of RCP 8.5. Serbia, which has currently 30% of its electricity comes from hydropower, will lose more than 13%. Romania, again, 30% of its electricity is generated from hydropower, will suffer almost a 13% decline due to climate change. Sweden will also lose out more than 12% in hydropower generation due to climate change. So, from hydro, which is where we worked on both global and European level impacts, we switched to wind power, which is another pillar of European renewable energy platform. So this is at the European level, and this is a joint work with Francesco Bosello. I'll move on. Wind energy currently accounts for almost 19% of EU's total installed power generation capacity. As you can see, the dark navy line, it's a constantly increasing path, right? And this shows total power generation capacity in the EU between 2008 and 2018. In 2018, wind power also covered 14% of EU's electricity demand. Denmark had the highest share at 41%, Ireland 28%, and then Italy is somewhere in the middle, about 6%. Some countries do not have any wind power generation yet. We use MHIRE's wind power generation dataset. This is a magnificent dataset in collaboration with JRC. We use this to conduct a both high spatial and high temporal resolution analysis. We have data for hourly wind generation data, which is a very high frequency data for 255 NUTS2 regions between 1986 and 2015. MHIRES uses reconstructed wind farm database to provide wind power generation at country NUTS1 and NUTS2 levels, but we, in this analysis, focus on NUTS2 level data. Full load hours across Europe. So wind power generation across Europe is rather heterogeneous. Sweden is the best performer. It's about 0.69%. Belgium is the worst performer at 0.12%. For climate data, we use ERF5. This is the 5th generation ECMWF atmospheric reanalyzed climate data, providing us climate data at single levels for every hour. So the final data set we used for econometrics had more than 67 million observations. So this is a massive data set. It's beautiful. Some descriptive statistics to focus on, but we will move on here. The regression. Again, we use a panel regression framework at the NUTS2 level, but we control for year, month, and hourly fixed effects. Our dependent variable in this case is the log of hourly wind power generation. The climate data or our climate variable of interest is the 10-meter wind gust. We also control for air density, as denser air exerts more pressure on the turbine rotors, which results in higher power input. Again, as I mentioned, we control for various fixed effects, both location and time. We use robust standard errors. But because wind power is positive, continuous, and right skewed, we use a gamma generalized linear regression with a log link. For the sake of time, I will move on. So this is the main result from the main specification. Our econometrics show that optimal wind speed maximizing wind power generation in Europe is slightly over 10.1 meters per second, which is approximately about 36.4 kilometers an hour. As you can see, beyond this threshold, there is a steep decline in wind power generation as the efficiency declines, and of course, at very high wind speeds, the turbines have to be shut down as they become a danger. We also find that power generation increases with air density. We segregate our data by seasons. We find that optimal wind speed maximizes wind generation during the summer in Europe is about 9.7, so it's slightly lower than our full panel. Whereas in the winter, we find that wind power is maximized at a higher wind speed of about 16.6 meters per second. Again, we have a battery of robustness tests, but I'm not going to talk about them individually for the sake of time. Projections. We combine our econometric estimates with future climate data.
Shouro, excuse me, this is Francesco speaking. If you can move to the conclusion in, let's say, 3 to maximum 4 minutes.
Okay. Please. So under 4.5, we expect that wind power generation in Europe to decline by about 5.6% by 2050 and by 7.3% in 2070. As you can see, it's mostly negative impacts, at least spatially, in Europe. For 8.5, which is the unmitigated climate change scenario, we expect significantly higher losses, about 7% by 2050 and almost 10% by 2070. The largest declines is expected in eastern and western parts of Sweden and in Andalusia in Spain. So now we're done with the energy supply part of climate impacts for COACCH. I will briefly present climate change impacts on energy demand in EU. This is a joint work with Professor Enrica Dachan. We know energy demand is increasing globally. We observed that final energy consumption has increased by 7.5% between 1990 and 2016 in EU 28. But of course, the energy sector, as we have just seen, is also heavily affected by climatic stressors. And of course, future climate conditions are likely to have a heavy influence on energy demand, either likely due to increased extreme temperature events, or on the other hand, demand for cooling services might decline due to fewer low temperature extremes. Some trends, I will move on this. What we do in this paper is, again, very similar to what we have been doing so far. We combine econometric estimates with high-resolution climatic data from regional climate models, or RCMs, again, focusing at the NUTS2 level. We do this at a sector and fuel combination. So we have 3 fuels focusing on electricity, petroleum, and natural gas, and 4 sectors: agriculture, industry, residential, and commercial. We do not estimate the regression coefficients in this paper, but we take them from the Dachan and Sewing paper published in the ERE journal in 2017. They use a global data set to estimate various semi-elasticities in a majority of energy carrier sector and region combinations. They find that the demand for energy increases heterogeneously with hot days across energy carriers and sectors. As I said, we combine this with 2 climatic scenarios, RCP 4.5 and 8.5, under 4 regional climate models to compute a multi-model mean. And again, we compare a scenario with climate change to a scenario without climate change. The input that we use as climate data is the difference in hot, so it's greater than 27.5 degrees Celsius, and cold, so less than 12.5 degrees Celsius bins between the historical and future periods. Why this is important, bins. The number of hot days in EU, which is a relatively cold region, is expected to increase under both the warming scenarios we consider. Some of the regions in Greece and Cyprus are expected to have an additional 30 hot days per year by 2070. That is 1/12 of a given year. What we find? We find that some significant increases in demand is expected under RCP 8.5 by 2070. Industrial sector demand from natural gas will increase by 11.4%, whereas service sector demand from electricity will increase significantly by more than 40%. We'll also expect that the expanding service sector and the share of energy demand from electricity will likely exert additional pressure on the electricity infrastructure. This is a policy finding. In the residential sector, energy demand is expected to decline from natural gas and petroleum under an unmitigated climatic scenario and by 2070. This is likely driven by reduced consumption for heating and fuel switching from petroleum products to electricity in the commercial sector and due to increased energy efficiency in the residential sector. So as I mentioned, we have a multi-combination scenario here. So we have 2 climatic scenarios, RCP 4.5 and 8.5, and we compute projections for 4 sectors and 3 sectors and 4 sectors and 3 carriers of energy. The results are heterogeneous. I will provide a few more examples before we move on to the conclusion.
Sure. If you can conclude, because we have hundreds of questions, so just 1 minute for the conclusion.
Yes.
Then
so
I will cut you off.
To the conclusion here. So we have, again, these beautiful maps, which unfortunately I don't have time to present. But so I will skip the conclusion for the energy demand part and move to conclusion in general of our paper. From energy supply to labor productivity, Europe faces an unprecedented levels of damages from climate change. We have combined spatially disaggregated data with high-resolution climate data under various warming scenarios. We expect hydropower generation to decline by 4.2% and more than 7% in 2070. We expect Slovenia, Croatia, and Austria to suffer the highest declines in hydropower. Wind power, one of the major platforms in EU's renewable policy, will decline by almost 10% by 2070 under 8.5. Energy demand from natural gas is expected to increase by 11% from electricity in the service and in the service sector by more than 40%. In our analysis, we have tried to identify hotspots in Europe that are especially vulnerable to climate change. And we hope that these results can be used to design and implement tailored policies to mitigate and adapt to these impacts in Europe and, of course, across the world. With that, on behalf of Jessie and myself, thank you for your attention, and we are open for questions.
Thank you. Thank you, Shouro. Thank you, Shouro, and thank you, Jessie, for the very, very interesting presentation, and that the presentation is interesting, or at least stimulating, is witnessed by the large amount of questions that we have. Of course, I have a difficult task to summarize the questions. Of course, I will not touch upon all of them. It is not possible. I will do my best. Anyway, let me say to our audience that question could be also addressed to our speakers afterwards. So we will collect them, and then they could receive ex post, let's say, an answer. So let me just start to pinpoint two very broad research, curiosities or questions that the by far the most voted, which is highly international, because I see Italians and northern people. I mean, Europe, all Europeans are asking this question, like Bjorn, Adrian, hi Adrian, Massimo, Marcus. The key issue is, how are you going to, or have you addressed the issue of adaptation? This is very important. So all these results, either in terms of impacts on agriculture, or say on value added per unit of workers, or all these impacts on energy, how much and how is it possible to take into account adaptation processes? This is the big question. Second, I'm just addressing you 3 points, and this is for both of you. Second, it is perhaps also related to this, important to explain our audience how, for instance, all the technologies that are part of the agricultural sector have been taken into account, or could be taken into account with this methodology, which is quite an aggregated sort of estimate, because agriculture, there are many types of agriculture, many types of crops, many types of technologies. So how this could be taken into account? Third question for both, you can decide who's going to answer, the issue of which kind of climate models are we using? What are our climatic data? Because this relates to how are we taking into account uncertainty. Okay, so let's just start with these 3.
Just if you want to take the adaptation one, I'll take the 2 technical ones.
Yeah, sure. Do you want to start?
Yes, please, Jessie.
Okay. So I could start with the adaptation. So it was a very interesting concept that we actually wanted to apply to our data. The problem was that we had somewhat of a trade-off in this analysis. If we wanted to do a subnational level analysis, the available data to us is only 15 years, which I think was rather short to observe adaptation changes. within region. So how adaptation looks like within the same region over time. So this was not a very possible option for us, so we opted for a subnational impact instead. So how adaptation is factored in here is that it's considered in the historical impacts as so the productivity of the productivity data of each region already includes some form of adaptation that they are currently implementing. The problem to us is that we do not have any, let's say, a clear variable into which this adaptation factor in the historical data can be projected into the future. So our assumption in the projections is rather that whatever they are doing now for adaptation is the same as what they are doing in the future. Yeah, and for us to actually determine how their adaptation strategies change over time, we would definitely want to see, or we would definitely need something that's longer than 15 years. Yeah, and over to you, Shouro, on the other two questions.
Thank you, Jessie. So the second question was about technologies in the agricultural sector. So first is that we're not focusing on crop yields per se. We're focusing on gross value added per active employee in a given sector. In an econometric setting, technological change is implemented via the time fixed effects. So we have the annual fixed effect, yearly fixed effects included in the regression, and that controls for technological change in a given NUTS2 region over time. That was the second question. The third question was on the climate models. That's a very interesting question, and I think we sort of glossed over it due to time issues. So for each of the papers, we computed a multi-model mean for the future climate data. So for the labor productivity, we used 3 models. For the hydro paper, we used 5 climate models, 5 GCMs there. For labor productivity, we used 3 regional climate models. For both the for the wind generation and for energy demand, we used 4 different regional climate models. So yes, absolutely very important to control for the uncertainty across the individual climate models. And we do this by computing an ensemble of multi-model mean from both global and regional climate models for each of our paper.
Thank you very much. I have now, let me turn to 2 questions which are slightly more specific, I think, for Shouro. And we have 2 questions from 2 different attendants. One is if you can explain or develop a little bit more what is the major driver of declines in energy production, energy supply in the northern countries. That was hydropower. And the second is related to wind. So what is the major driver of the wind results? So are you considering more an issue of wind speed or something that is related to changing, let's say, pressures, atmospheric pressures? So what is the major driver of the result of wind? Is the wind speed or constancy?
So I'll start with the wind. So for wind speed, we control for the wind gust, the 10-meter wind gust, and air pressure, and we use both these variables for projections. The decline is largely driven by the wind speed variable going into the future. As for the drivers of hydropower generation declines in Europe, one issue, so the major climate driver is obviously the drought events we expect. So the hydropower generation results are largely driven by increase in the frequency of drought events in the future. But for hydropower, we must also remember that hydro plants tend to be older and they have expensive environmental impacts, and of course they're expensive to maintain. So all this in combination, so the increase in the frequency of dry events, maintenance of hydropower plants, and the fact that they tend to be older than in compared to, let's say, wind turbines plants, largely drive the declines even in the advanced countries of Northern Europe.
Okay, so just let me pick up a couple of more questions. Yes, a more general question on perhaps let us move a little bit on policy implications. So both of you could give an answer to this kind of question. That is, okay, we have this decline, for instance, in hydropower supply. Did you in the study already take into account the possibility that there are some switches across different kinds of renewable generation? This is the question, and of course it is just to clarify to our audience. The other is more in general. Can we think about some kind of alternatives of our action to cope with this reduction? Because basically we have a reduction also in renewable energy production, at least this kind of this specific form of renewable energy. So what could be the implication for this? So this is a more open question for let's say the debate. So I would say Jessie first and then the Shouro afterwards.
Yeah, so in terms of labor productivity, possible policy implications is, first, it has it provides some scientific evidence on where to prioritize certain investments and where to prioritize certain measures to protect certain sectors in different areas within country. So we already see that there are certain parts of a country that's more at risk than the others, and so this directs so provides evidence for policy to direct some investment in certain areas. Another thing is that in terms of sectors, so if an area is rather investing so much on a specific sector that's very climate sensitive, and as we have seen, there are sectors that are more at risk than others in certain areas, then it's also rather a signal to maybe there would be other areas within the country that would be more productive in terms of this specific sector. And yeah, so it's rather a adaptation in the sense that yeah, not so basically strategically placing your sectoral production on where you can avoid climate impacts. Yeah, so on to Shouro.
So yes, there is a specific question about whether we control for switching. Yes, we control for electricity production mix. So we do control the share of generation for each country in a given year. So if they increased in one, obviously the share of the other four declined. For policy implications, from the fact that we expect even renewables generation to be negatively impacted, I think we have identified hotspots that are especially vulnerable, as Jessie mentioned. I think it's time for tailored policies, tailored investment policies. We have to focus on renewables. We cannot go back to the coal power days. No. So the policy implications for EU in general and countries also is to adapt to these changing conditions and invest in technology in renewables. This is the major policy implications, that we cannot go back. We expect changes. The changes will occur. We have to mitigate them and adapt to them.
Okay, thank you. So let me now conclude and also apologize for the those who have not seen their question addressed. There are really many and technical. For instance, the role of glaciers. I mean, many point of discussion. Of course, we cannot address them all today. Just let me conclude with these two comments that let me the opportunity to briefly say something myself. The comment by Iqbal and Justine. More or less, both are asking for the availability of results from the COACCH project. Justine, we are not developing index or indices for climate and labor productivity and energy, but however, we are going to, one of the output of our project will be an online tool where the and an online database. So we have two different tools to share our all results in a totally free and totally public for non-commercial use, of course, because you cannot get rich with our work. Just a joke. But this will be both will be totally free and public for everyone. And this also answered the question from Iqbal, saying that these are the most the way in which we are going to interact as much as possible. So with also with the academics, the academia, and the public, but also with other projects. So all our data will be available to the research community and also on also projects and activities which are going on. So with that say, let me thank you again for joining this webinar. Let me recall that there is another one on Monday, but we are going to have other two webinars specifically related to the COACCH results, which will be later on. Let me thank you again for attending. And in particular, let me wish the best in these troublesome times, and hope that perhaps we can join a big conference with a lot of people participating in person as soon as possible. So thank you, Shouro, thank you, Jessie, and thank you to you all.
Thank you,
Bye-bye.
everyone. Bye-bye.
Bye.